All right, folks. Well, this time around, I want to take a look at smart pointers specifically in C++. So last time we looked at the theory for smart pointers. This time we'll look at one actual implementation of these things. So we'll run through some discussion, and then we'll take a look at some actual code. So the idea is the smart pointers in C++ are called shared pointer. This is a templated class. So again, you can create a shared pointer for ints, a shared pointer for nodes, a shared pointer for strings, a shared pointer for whatever your class happens to be, whatever your dynamically allocated resource is going to be. These are located in the tr1/memory standard library. So we'll have to hash include that. And again, the notion is that these smart pointers, somewhere inside them have reference counts that keep track of how many smart pointers refer to an item at any given point in time. And they also maintain internally a regular old dumb pointer to where the thing actually is in memory. And again, the programmer never gets direct access to the memory address of the item that you're creating and getting rid of. When you're going through and using things like the assignment operator between smart pointers or the copy constructors, right, passing these things as parameters and whatnot, again, it goes through and updates the reference counts for anything that either of the smart pointers involved point at, right, the source and the destination. And again, as we discussed in the last time, it automatically goes through and deallocates the resource when the reference count hits 0. So this is pretty much exactly the layout that we were talking about in the previous video. So syntactically, again, we've got to hash include our tr1/memory. And when we want to go through and create one of these things, right, they're in the std library. So in std, in tr1, we want to create a shared pointer. Again, this is a templated class, so we have to say a shared pointer to what? So let's say I've got a list class, and I want a smart pointer to a list. Then I'm saying, okay, I want a shared pointer to a list, and then whatever your variable name is going to be. So pointer A here is just a smart pointer that can point at a list. Of course, it doesn't yet. We've created the pointer, but we haven't made it point anywhere yet. So if we want to, we can create a request to please go off, create a new list, and make A point to it. So this reset method is the one that makes the pointer point someplace new. So if you call reset by itself, it just clears the pointer. If we want it to point at something in specific, we can do something like this and say, okay, please create a new list and make pointer A point to it. So this would be creating the new list, running the constructor on our list someplace, and then creating an internal pointer to wherever that thing got allocated, and setting a reference count to 1 for that, because pointer A is now the one and only thing that refers to that item. When you want to get at it, you use the regular old dash greater than operation for getting at a method or a field through a pointer. So if I wanted to do an insert on my list, I'd say, okay, well, through pointer A, call the insert method on the list that the smart pointer refers to, and pass it whatever parameters it expects. Right? So regular old access. And again, behind the scenes, what this is actually doing is saying, okay, let's make sure that that list actually exists and that it's safe to access it. We can do copy operations. Again, it can do things like pointer B equals pointer A, or pass our pointers, smart pointers, as parameters. And again, it's going to update the reference counts appropriately, up or down, whatever needs to happen. You can clear or nullify a smart pointer, make it point nowhere. So it's just your smart pointer dot reset, right? The reset method. And again, this is going to decrement the reference count for whatever A used to point at. So those are the basic operations. There is another one that's closely associated with this called a weak pointer. So for the shared pointer, right, everything you're doing is updating the reference counts, automatically deleting items when the reference counts hit 0 and whatnot. There is also a weak pointer that lets you access an item but doesn't change the reference count. So essentially, if you've got a copy of something, if you want a pointer to something that you want to say, okay, well, here's a pointer to it. If the thing still exists, I want to do X with it. So it still allows controlled safe access, but bypasses the need to do some of the reference count updates. So we're not going to play a lot with this, but just so you're aware that they exist, the syntax is pretty much the same. You can declare something as a weak pointer to an item. You can set it from a smart pointer, so we can say my weak pointer is equal to whatever my smart pointer points at. So now the weak pointer also points at this thing, but it's not updating the reference count for that item. But since it's not updating the reference count for it, we have to make sure that before we try and access something through the weak pointer, it's actually safe to do so. So the weak pointers have this lock method that basically say, okay, well, try and get access to something. If it exists, I'll give you back the actual smart pointer for the thing. If it doesn't, I won't. And essentially return a null if you if that thing is no longer accessible, if it has ceased to exist. So typically what you'll wind up doing is saying, okay, if I want to get at my list, for instance, through this weak pointer, then I'll create a temporary smart pointer for it. I'll initialize it through this call to weak pointer lock. So again, the idea is if the thing exists, this operation succeeds, and I can use my smart pointer to get at it. If it doesn't exist, this fails, and we just move on and do something else. So again, it's not something we're going to play with a lot, but if you start looking through code and examples and whatnot, you're probably going to run across weak pointers somewhere along the line. So this is a little bit of what's taking place there. All right, in terms of the code, I wanted to just have a quick look at sort of how this stuff looks in C++. So usual idea, we've got a little smart pointer example here. So we'll just take a look at the code in this. And so what we've done is created, just so that we've got something to access, we've created a little toy class here, myData, just something for us to dynamically allocate and deallocate. And there's nothing too exciting about this. We can pass a parameter to initialize it. It's got one data field in it. When the constructor runs, it prints a little message saying the constructor runs, just so that we can see what's happening. When the destructor runs, it says the destructor is running. And there's a get method, so I can get at whatever data is actually in there, just so we can play with it a little bit. So if you notice, we're remembering to include our tr1/memory library up there. And what we're going to do is print out a little message saying, okay, we're about to try creating one of these things, and we'll go through and create a shared pointer for one of these data items. So sPointer is the name of my smart pointer. I'm going to initialize it by creating a new data item, and I'm going to say, okay, use 10 as your data value in that. If you go back and look at the optional parameter for our constructor back there. So initialize the data item with value 10 and make the smart pointer refer to it. Then we're going to go through and create a second smart pointer and initialize it from the first one. Right? Make it a copy of the first one. So in theory now there's two things referring to this data item, so it should have a reference count of 2. And then we'll just throw in a couple of printfs to make sure that these things actually are pointing at the right item. And then we'll create a second item and make that second pointer point, or the first pointer point to it. So we're going to make the first one point away from the original item at a new item. So now in theory, the reference count for both of these items should be 1. Right? The original pointer is pointing at the new one. The second pointer we created is pointing at the old one. And then we'll just do a couple of printfs to make sure that actually works. We'll try nullifying that second pointer. So nothing is pointing at that second item or that first item anymore. Our original item has a reference count of 0 theoretically. So in theory, we should see the destructor for it run at this point. And then we'll end the program. And again, in theory, the The other smart pointer, the original smart pointer, should cease to exist now, and we should see the destructor run for the second item. So that's what we should see happening here. Whoa, what did I just do? Let's try that again. So let's just make sure that that's actually up to date. And we will run our code here and just see. So again, we're creating that first item that we initialized with 10. So we can see that the constructor for it ran. We hit those two printfs that printed out the current value. Sure enough, both the first pointer and the second pointer are both referring to it. We did that second new operation where we made that first pointer point at a new item with a 20 in it, and sure enough, the constructor ran. And when we threw in the two printfs, the first pointer is pointing at the new 20, and the second one is still pointing at that 10. And then we reset the second pointer, and sure enough, the destructor ran. So it did realize that the reference count hit 0 and ran the destructor automatically. And then we ended the program, and sure enough, the destructor for the other one ran too. So you can see that this stuff is actually working, and you've got a bit of a syntax example for how it all fits together. All right, I think that's where we will leave our dynamic memory handling. We will pick up, I think we'll move on to classes and objects and abstract data types and whatnot in the next of our videos.